Okay, great. So first of all, my apologies, everyone, for the mix-up, and thank you very much for attending this talk. My name is Zainab Titus, and I'll be talking on how we've used neural networks to condition surface-based geological models and how we apply this for uncertainty analysis in the subsurface. So this work was done in collaboration with the following authors at the Department of Earth Science and Engineering at Imperial College London. So the motivation for this work is that we have different techniques, different methods for generating geological models and conditioning these models to honor observed world data. However, for some of these techniques, there are advantages as well as disadvantages. So techniques such as surface-based geological models enable us to still retain and conserve geological realism, such as seen in figure 1 here. So as you can see, this is grid-based method where essentially we discretize a domain into grids and then use that to define the geological architectures. However, as we can see from here, we lose information. We do not conserve geological features such as channelized bodies and interconnecting bodies. While with using surface-based geological models, we're able to conserve geological realism. So this gives us that advantage. And also, there are more complicated methods than surface-based models, which allow us to conserve or preserve geological realism. However, these are very computationally expensive, more computationally expensive than surface-based geological models. And so conditioning these models as well as generating these models is not very time efficient. So that is the motivation. We can use surface-based models to generate geological models that actually preserve geological features, but as well enable us to do this within a fraction of the computational expense for other more complicated methods. So essentially, how do we apply surface-based models in geological modeling? So surface-based models use parametric grid-free surfaces to model geological geometries. So as we can see here, essentially we define control points and use spine interpolations to model our geological architecture. So we can model complex features such as boundaries between layers. We can also define volumes by using surfaces to define these volumes. And within these volumes, we can actually have petrophysical properties that are uniform, such as the porosity or the permeability of our rock types being uniform. So essentially, it gives us a flexible way of manipulating our models to really adapt these models to retain geological realism. And an important thing is we can do this quite rapidly. So this enables us to use surface-based models using the NURBS approach here that are grid-free and parametric to rapidly generate models, multiple realizations that we can use to train the neural network and develop an approach for conditioning these models. So this is just an example of how in practice we use surface-based models. So for example, here we have a depositional environment, a marine depositional environment. If we take a 2D slice, a cross section through this domain, we can see here the various rock layers, the various log types, and the facies types. So the facies types just indicate the rock types. And well, to model this kind of geometries with surface-based models, we use templates such as shown here in figure 5A and B, where essentially we define control points that we construct using various parameters such as the height, the length, the deep angles from the geological features that we want to model. And then we use this to construct the surfaces that would essentially define our geological models. So this is how we use our surface-based modeling approach using NURBS to generate multiple realizations for conditioning surface-based models. So as we can see here is an example of a surface-based model. So essentially the degree of the curve here is 1. So we've just simplified the previous image here for testing our approach. So what we have here is the geological model where we can see different layers and we can see different bounding surfaces in the subsurface. And essentially to construct a model such as this, we need just about 240 variables that define different parameters like the height, the width, the depth, angle. So these surface-based model has 240 inputs, and these serve as the inputs to our network when we're training the model to be able to predict, say, the facies type at a particular well location shown here. So essentially what we do is we train neural network to understand the underlying process of generating surface-based models by mapping a set of inputs, which in this case 240, to a set of outputs, which in this case is a facies type, along different discretized locations at the well location. So we are employing a supervised training mode here. So this is how we are able to train the neural network in the forward modeling process of generating surface-based models. So this, in an earlier work, we did that, but just to highlight how we do the conditioning. So essentially what we do, like I said earlier, we train the neural network to understand to learn the underlying process of generating surface-based models, and then we test our network. So this essentially is our forward modeling process. But in the inverse modeling, where we are more interested in conditioning, say, randomly generated surface-based models to well data, what we do is essentially with our trained model, we use that to predict the facies type. That's the outputs that I showed earlier at the well using stochastic initial inputs. And then we calculate the mismatch with the predictions and our observations, which is our reference model, which is our information for the reference well at the same location that we want to condition the models to that data. And essentially, we do this iteratively, and then we apply other constraints, other criteria, just to evaluate the correlation with our predictions at the well from the pre-trained model, and also the observed data. So this is just a classic inversion procedure that we do. We do this iteratively, and based on our criteria that we impose, we add this model to our condition suite of realizations, and essentially we're able to then understand spatial variations based on the results from the conditioning process, or what we refer to as the inverse modeling in this case. So this is the approach that we've used, and in previous work we've seen. So this result just shows for the forward modeling, that's just training the network to take in the surface-based model inputs and predict what the facies type along different locations at the well will be. So we were able to do that, and we're able to demonstrate that we can do that to a reasonable degree of accuracy from the results shown here. So these are different surface-based models where we've sampled essentially 3 wells, and we've trained a network to be able to predict the facies type at those 3 wells, and we can see that we're able to do that reasonably well. So with a model that has a high degree of accuracy, we're then able to perform the inversion that I explained in the previous slide, where we use the pre-trained model and calculate the mismatch and iteratively update the model inputs. So this is the result of the inverse modeling. So what you can see here is we have an initialized model, and then we have a reference model, and then this is the optimized model from the approach using the neural network. And as we can see, we don't have an exact match over the entire domain. However, when we look at what particularly happens at the location where we have data and we're conditioning these models to, we can see that we have a reasonable match here based on the metrics, the correlations, and also the criteria that we impose and we use to condition our models. So this is what we're able to achieve from previous work. And the important thing about this is, like I said, is for understanding uncertainties. And here what we can see is we can see the maximum predicted facies at discretized locations for our initialized models. And essentially, we don't really see patterns being captured here. So we don't really see variations, in among these models. However, with the condition models, we do the same thing. We predict the maximum fishes at different locations, and we're able to see that at well locations, we're actually capturing patterns and observe geological trends that we see based on our conditioning. And when we also further analyze these spatial variations in terms of the uncertainties, so what we have here is what we call a frequency of predictions plot. So essentially, this measures the agreement between our models. And what you can see here in the first plot is for the initialized models, we don't really see variations laterally. We don't see a lot of information. However, when we look at these models after we've conditioned them to data, we can see that at locations where we have well data, there's less uncertainty. And yeah, the importance of this is for a geologist, for a geoscientist, a reservoir engineer. This implies that where we build models, we're more confident in placing our wells where we have lower uncertainty, or we will need to place more wells where we have higher uncertainty to further reduce the uncertainty in the subsurface models. So this was an earlier work that was done. However, the limitation of this model is it didn't give us the flexibility to change our well trajectories, and as well we needed to be able to train a model that will allow us to put multiple wells and not just a fixed number of wells to better understand uncertainty. So we decided to take a different approach where instead of sampling just certain well locations, we then decide to sample random points in the domain and essentially do the same approach where for each point we have the each point in this case becomes an example in our training data set. So we have in this case not just the 240 variables for the inputs of the surface-based model, but we also have two additional inputs that define the location of each point, and then we predict the fish's type at that point. So we just sampled random points within the model domain for lots of models, a lot of models, and as you can see, this just shows the distribution of the randomly sampled points and given their coordinates in the x and y directions. And this is the model architecture. These are the hyperparameters for the model that we trained. And I think essentially one thing to understand here is what maybe jumps out is that there were a lot of examples used. However, these are grid points. So essentially, if we use 20 million examples, we can say that is equivalent to 20,000 examples on a 10 by 100 grid. So yes, this is how we were able to train the model for this next approach where we wanted a more generalized model, and we simply use the cross entropy loss function for classification, the classic function. And this is the result of the training. So we can see the results. And so the results we achieved here are comparable to the previous results of the other model where we were able to train for a particular for fixed locations in the domain. And yeah, the model took much longer to run. We were using more examples, and it was a larger model, a deeper network as well. So this is just the training and the loss and accuracy plots for the network, and just to show some examples of the predictions. So as you can see here, what we have is we have a deviated well, so it's a varying well trajectory, and we can see that essentially we can take any point within along this well, and we can predict the fishes type, the rock type. And what we can see, what we've done here is essentially we've just taken sampled points where the surfaces intersect the wells, because this is what we will typically see when we take a well log, of the subsurface. We'd usually see where the signals change based on change in rock types. And we can see that our model predicts with reasonable accuracy. We can see another example shown here. So this is for the forward modeling, where we are able to predict fishes type at surfaces intersecting the well. But with this method, essentially, we can predict the fishes type at any point in this within the domain. So this is the results for the conditioning. So just as we did previously, we applied the same approach to condition the wells to the models to well data. And what we can see is we start off with an initial model, and this is the reference model we want to condition the network, the model to, and essentially we're able to achieve reasonable accuracy based on the conditioning. So another point to note is based on the criteria that we impose for different samples or different randomly initialized inputs that we want to condition, we iterate for different number of times. For some of these examples, we take about an hour for one conditioning. However, this can be done in parallel, which is the value of the approach as well. And for some, takes just a couple of minutes. So it really depends on yeah, the conditioning, and as well in some cases how we initialize the models if the initial inputs are close to what the reference model also has. So this is for the conditioning. Now, to understand the uncertainties, which is really the value of this approach, we start off with a reference model as shown here. And as shown here is the maximum predicted facies type for randomly initialized models. And what we can see here is, yeah, we don't really see patterns, geological patterns being captured for randomly initialized models. And this is also the frequency of predictions plot for the randomly initialized models. We start off with using deviated wells instead of just vertical wells. And we can see that we begin to capture patterns in the geology. We begin to capture some features, particularly at locations where we have the wells. And we can see here also that our uncertainty begins to reduce where we have the wells. When we also apply this approach for a case where we have a horizontal well, we can see that along the well, we actually have lower uncertainty. If we compare these two images, so the previous image I showed this, and this when, sorry, so this when we have just one well, and this when we have two wells. So this is a horizontal well. We can see that we also have reduced uncertainty in other regions, which I think globally we begin to also reduce uncertainty in the model. However, it's more interesting if we look at what happens when we place our wells at locations where we have the highest uncertainties, and see how that applies to reducing uncertainties. So this is really how our approach helps us in reducing uncertainty, not just in locations where we have wells as well, but globally we begin to see reduction in uncertainty in other areas as we begin to constrain the model more. So this is the initialized model. Actually, these are the initialized models that we start off with, and then we end up with a case where we have just two wells, and we're able to reduce the uncertainty for a number of conditioned realizations. So this is a very flexible approach that enables us to understand the uncertainties within our model, and also to be able to understand how we can use this information to improve reservoir performance by placing wells where we have higher uncertainty to gain more information, or placing wells where we have low uncertainty to be able to extract more resources from the subsurface. Um, in conclusion, I would say we have an approach that is general for our own application. We're able to condition surface-based models to observed data with wells of varying trajectory, and this approach enables us to generate models that are conditioned to well data and also honor geological realism. And also we've been able to see that with this approach, we're able to assess uncertainties and also compare what happens where we have multiple wells or varying well trajectories. The further work, future work for this would see adapting this approach to actually explore the sequential data, sequential arrangement of surface-based geological models. So the models I showed earlier, we, if I can just go back, we have, so the models are generated. So as we can see, for example, in in this figure, the models are actually some sort of sequential data that we can also see or use as time series data. And it will be interesting to explore how we can use other networks such as recurrent neural networks to perform this sort of modeling and also the conditioning for this. And as well, the next step will be to look at 3D models and how this would perform in an approach to actually make it a method that can be applied for more realistic geologies. So thank you very much for listening. These are the references, and thank you again. And I would like to acknowledge the sponsors of this research work, and I'm happy to take any questions if there are.